All right, I'm not going to present any math today. I want to, but I need to kind of set the stage before I do that. And the what what I was what I want to do is talk about what it means to have an end-to-end or higher level perspective of large scale deployments, and I mean very large scale deployments, in such a way that we can do prediction on the behavior of large scale systems. And I want to talk about why the mobile process calculi, and in particular a flavor or variant of the row calculus, is going to be important for that kind of view. So I want to set the stage by bringing up an example. So let's think about a social media kind of thing like Facebook or Twitter or Instagram, and think about a single post. So a single post you might think of associating a smart contract with that, because you could think of the post as traveling from one agent to the next, propagating itself around the network. And as it does so, the engagement with that post, so collecting likes and collecting other forms of engagement. For example, it might collect it might collect tokens, not just expressions of sentiment, but actual tokens. And we want to be able to think about how the collection of those tokens for a single post is related to the multiplicity of that post, right? So it might be that we think about it kind of biologically. So imagine that a post appears in the feed. I make a post on a social network that is running on top of our chain. And then that post appears in the feeds of people who are following me on the basis of a variety of calculations. And then those parties, so let's say, just for example, that Steve and Ian and Raphael view that post in their feeds and they engage with it. So then, Steve might like it, Ian might, like it, and then Raphael might say, now this is really important because it's related to my work. And so I want it to have more visibility in the network. And because I want it to have more visibility, I'm not just going to like it. I'm going to put my tokens where my mouth is, and I'm going to put some tokens into it. And because I'm giving it tokens, it's effectively giving it energy. I'm boosting the signal, so to speak. And this is very much the way Facebook is working today. You can in fact boost posts that you want to have more visibility. So it's a natural thing to do, and there can be a whole range of economic activity around this, so that people are engaged in not only the ability to spend tokens that boost information flow, but receive tokens as a result of the way they have participated in the information flow. So before I go on, I just want to make sure that scenario, that sort of use case makes sense to people.
That makes sense to me.
Yes, following.
Okay, cool. So because the post itself kind of has a life of its own in terms of its path through the network, it makes sense for it to be a kind of agent in its own right. So in other words, in Rolang or R-chain terms, it's got a smart contract. And that smart contract may manage a wallet. And then we have to think about multiplicity versus single versions. So you run into interesting bottlenecks if there's only one copy of the post that is serving all of the engagement, right? So if you have exactly one entity that has to serve Steve and Ian and Raphael, then if the engagement is potentially subtractive as well as additive, then you might want to put it into a single entity so that you can manage the resource or state associated with that entity. On the other hand, if everything is only additive, right, so people can only like, all right, or only give some kind of expression of sentiment, or they can only add tokens, but they can't take tokens away, then you could have multiple instances and you could do aggregation later. Does that make sense?
I understand the adding later, but the aggregation piece was, I'm looking forward to getting clarity on that piece.
Okay, so let's imagine that instead of having a single instance of a smart contract that's serving, so Greg posts, and instead of having a single instance of the smart contract associated with that post, there's a copy of the contract that shows up in Steve's feed, and a copy of the contract that shows up in Ian's feed, and a copy of the contract that shows up in Raphael's feed. And each one of them is independently collecting the likes and the tokens. But later, they may all aggregate because they're all sort of children or copies of the original post. Does that make sense?
Yeah, I guess as far as, you know, the point in time of when the aggregation occurs. So I'm assuming that it's not, you know, it's probably asynchronous, you know, everything's in flux. So long as there's aggregation, I guess it sort of aggregates over a period of time as opposed to a single point in time.
That's correct. You have a kind of eventual consistency.
Okay.
Right,
Yeah.
but the main point here is not sort of the consistency model so much as the fact that there's a design space where there's lots of trade-offs in terms of performance and perceived responsiveness versus management of state. Does that make sense?
So you're saying if we have multiple instances, for example, it's difficult to subtract something, right?
That's correct.
Much easier to just okay.
Yeah, much easier to just add, right? But then if you want so if I, as a client of the system, want to look in on the performance of my post, I want to see the global view. Does that make sense? Right.
Yes.
Right. So I like to know that you know over the propagation of the post, what's the total engagement or the aggregate? You know, how many tokens has the?
Okay.
Yeah. Does that make sense?
Yeah. Now that I need that illustration. That's helpful. Okay.
Okay. Great. So now let's talk about the numbers, right? So imagine that it's not little old me, you know, who's primarily invisible in the world, but it's someone like Elon Musk. So Elon Musk makes a post and he's got 10 million followers. And so now we have potentially 10 million instances of the smart contract that's serving that post. And now if we think about all of the influencers on the internet and all of their their posts, we're talking hundreds of millions or billions of smart contracts running. And so what you'd like to do is to be able to have predictive analysis of the entire system. And it's not just limited to these kinds of social media situations. You could imagine that the same thing is happening in a logistics kind of application, right? So, you know, there's probably millions of packages or tens of millions of packages per day that are flowing through in any one of the large scale logistics companies such as UPS or the USPS or the Royal Mail or DHL, any of those, right? And each one of those needs us, if we were going to model it on our chain, we would model having a smart contract instance associated with the lifespan of a package running from, you know, dropping it off with the shipper to the receipt of the client. Does that make sense?
Yes.
Yes.
Follow.
Okay, and so again, the numbers and scale that we're talking about, you know, are millions of packages, you know, on a daily basis. Many of those shipment requests will last multiple days. So at any one time, you will have hundreds of millions. This is a conservative estimate, hundreds of millions of smart contract instances. And so what you'd like is to be able to have an end-to-end view of the system so that you can do resource planning. You'd like to say, okay, when the processing gets to this shard, we know that this shard is going to have this kind of load. And so we need to make sure that there are this many validators at a minimum with this level, this kind of service level agreement engaged to be able to support the load during Christmas, for example. Or we're in the middle of an election cycle, so we know that the social media engagement is going to go through the roof. It's going to burst. And as a result of this bursty behavior, we need to do resource planning, right? So we want to be able to do it at the level of the system. You know, it's like the hardware necessary to support a smooth, uneventful, responsive experience. But also, we want to be able to make predictions globally about end-to-end behavior. So we'd like to say that, for example, we're seeing this kind of engagement on this post. And so because we're seeing this kind of engagement, we can predict things about its life cycle. Like it's more likely to get likes than tokens, or it's going to get this kind of combination, linear combination of likes and tokens. It's likely to have this kind of reach, things like that. So end-to-end predictions about the global state. And I don't really mean global in the, all I mean is that when I say global, I'm really thinking about a kind of transitive closure, because for all we know, in the not too distant future, there might be a shard of our chain running near Proxima Centauri, and they're running in a different namespace. And so, you know, what we're thinking of as global is hardly global, because there's this whole other, you know, Web3 over on that distant star. And I'm using a funny example just so that people understand that there's never going to be a global perspective. But there can be perspectives that are wider or bigger than the level of a single smart contract or the level of a single shard, et cetera. So does that make sense?
Yes. May I ask,
Sure.
Now that you mentioned, I was thinking about what sharding means, and it's basically like connecting two or multiple states. So that when you say transitive closure, do you mean something like that? That there is like some kind of bridge.
Well, what I think about in terms of a shard is a shard is defined by a couple of things. One is a community of validators, all of whom have to be consulted with respect to the consensus, right? So if so, I've got some machines and all of them are bonded and participating, and I've got some other machines and they're not participating, right? And so they're not in the shard.
And from the perspective of state,
so then the state that that community of machines is consensing on, that's the state, and that state will be partitionable, right? That's kind of the whole point of block merge, is that we can detect natural partitions in the state.
I mean, when we have partitions, and if we have consensus on some shard, basically we are interested what we can do between shards, right? We cannot see the global state, so we need somehow to connect these pieces of states, right?
Yeah,
so,
but so
that
go ahead.
Shard basically must be connected. We at least need to connect two shards to make it for this to be useful, right? Or,
for what to be useful? What's the referent of this?
For shard to be useful.
Oh,
because
no.
if one shard.
I understand what you're saying, but that because the model is uniform with respect to the inside of the shard versus across shards. So intra-shard versus inter-shard, it's the same mechanism that gives us all the goodness. Then then the utility of the mechanism happens even inside a shard, and it's because it's the same mechanism, right? It's namespace plus participation and consensus, right? But you get higher levels of utility once you go from intra shard to inter shard.
I see. Yeah.
But that's a great question, and I appreciate that. Okay, so what I've tried to do is to set for you the stage, give the setting in which this higher level view is important, right? And sort of motivate why we want to climb up. And then I want to point out that in today's environment, there is no such view. Amazon metrics do not give you any internal view of the programs that are running on Amazon servers. You cannot make system-wide metrics across Amazon in terms of the business logic of the clients that are using Amazon. Does that make sense? And there are good business reasons why that is the case, right? Because if Amazon had that kind of visibility, then it would be breaking all kinds of privacy laws.
So the view that a enterprise such as Amazon has now is more regional or fragmented. They're looking at the individual components, but they're not able to sum them up for a system-wide view.
No, it's not because of the regionality. It's because of where the boundary is. So for Amazon, the units are hardware, so machines, racks of machines, data storage, racks of data storage, connectivity, that sort of thing, and then containers that virtualize that functionality. So virtual machines, Docker containers, virtual storage. So that's what Amazon provides to its clients, and that's what Amazon can make meaningful metrics about. Amazon can't go into the C# program that's running inside the Docker container. And if they could, then the application that was running on Amazon would immediately sever their contract with Amazon, because it breaks a business level separation.
So the idea is to go to an even deeper granular level to get get those metrics, which is a truer indication of the overall system view that we want to look at.
Correct.
Okay, because if we're just looking at the containers and the Dockers and so forth, it's not a true indication or true report of what the overall system is. It's just not fine-tuned enough. To get the true perspective, you have to go deeper to a deeper level, and through this through this perspective, or through what you're talking about now, can get us there.
Right, but I want to be careful about language. It's not about true. Amazon is providing well, to the best of our knowledge, what one hopes that Amazon or AliCloud or Google Cloud, they're providing a true and accurate representation of the things they have visibility on. Right. But they cannot, because of business separation, provide an accurate or semantically useful visibility to millions of instances of a C# program that might be running in order to serve up a logistics app or a maps app or whatever it is.
So are you saying the reason why they can't get to this deeper granular view is not because of a technical issue? It's more of a privacy and legal aspect that's preventing them from getting this?
I'm saying it's both.
It's both.
They don't have the technical apparatus to do it. And then supposing that magically they got it, then the clients wouldn't want them to have it.
Okay.
Right? Because then Amazon would see too much about their business.
Right.
And so what happens is, because there's no uniformity across the industry, every large scale app is attempting to provide a set of meaningful metrics, but they're all bespoke. Right? Because you've got some people writing on .NET, and some people writing in Java, and some people writing in Python, and some people writing in Erlang, and yada, yada, yada. Okay? And so each one of those is trying to collect business meaningful metrics without a global view of how to collect those metrics or how to turn those into meaningful or useful predictions. Does that make sense?
So this aspect of bespoke processes that are going on. So there's no standard or commonality because there's no standard. They're each doing it a different way. Maybe you're using a different measurement or something like that. So they're not able to come to an agreement as far as collectively as far as what the overall view is. That's
right. And moreover, it hasn't occurred to the community at large that there might be a uniform, high utility way to collect metrics in such a way that you could make meaningful predictions.
Good. And I kind of see where this is going. So yeah, it's kind of like someone telling you the punchline to a joke before you hear the joke, or how
Yeah,
the movie
exactly.
ends.
Yeah, that's exactly right. So now with the mobile process calculi, and in particular with stochastic or probabilistic variants of the mobile process calculi, in which you map probability distributions onto winners of the race or winners of races. Now you can make accurate predictions of large scale systems. And we know that this is true because it has already been applied for the last 20 years to biological systems. So for example, back in the late 90s, early 2000s, Ehudi Shapiro and Bill Silverman and a few others started using a stochastic version of the pi calculus to model basic chemical reactions. So they're taking populations, large populations of processes that model sodium and putting them in parallel so that's a big parallel composition of processes representing the salient, pun intended, behavior of sodium. And a big parallel composition of processes representing the salient behavior of chlorine. And then you put those two populations in parallel composition together, and now you get a reaction. Individual sodium processes will find and interact with individual chlorine processes. And so there's mass action stoichiometric behavior that we know from chemistry, completely independent of process calculi. We can write down the stoichiometry in forms of differential equations and get predictions about the concentration of salt given a certain concentration of sodium and a given concentration of chlorine, and information about the relationship between temperature and other conditions and the reaction rate. And what Shapiro and Silverman and many others showed was they get exact accuracy. So they can make the process calculus models give exact predictions that line up with experiment.
Wow. Amazing.
Now, what people hadn't noticed, but what I noticed immediately was, hey, we can apply this to enterprise planning. We use process calculi, we use processes to represent the behavior, for example, of a package in DHL. And we know that there are other processes that are going to interact with that package, right? So a particular truck process is going to interact with that package. It's going to pick it up, take it out of circulation, and then when it delivers it to the next leg of the trip, it puts it back into circulation for some other process to interact with it. This is just like a chemical equation. And so with a stochastic or probabilistic version of the process calculi, we can climb up a level to the behavior, the system-wide behavior of processes. So we could have millions of smart contract instances that represent a given post. And we can have millions of instances of user processes that are, or feed processes that are interacting with the post. And we can use the machinery of the stochastic versions of these calculi to give us predictions about the end-to-end behavior of the system. Does that make sense?
Go
ahead.
Yes. I'm thinking when you say if we are modeling some chemical reaction, how many processes we want to create, or how to, when you say prediction on some social post, how we can decide how many how difficult or how complex computation we need to execute to have.
So, yeah, so that's great. That's a great question, and that comes down to representative sample, right? So we know what it means to have a representative sample and how that correlates to experimental observation, right? So all the things that we do in sciences like chemistry and biology and physics can now be taken over into the enterprise. So you can make predictions at a system-wide scale. You can observe the behavior of the actual system. You can compare it to the predictions of your model and then check to see how good the correspondence is. And then if it's wrong, great news. It means that there's some refinement or some subtlety in the correlation between the model and the actual system that you need to understand. Does that make sense?
Yes, yes. I'm thinking if is this model somehow similar to training some machine learning?
No, it is not. No, that's the whole point, is that a machine learning algorithm is a black box. Once some CNN or some other form of deep learning has been trained, you don't know why it behaves the way it does. With these models, you can exactly decompose it. And you can once you have an equation like, Na in par with Cl produces NaCl, right? You can not only make predictions using that, you can also turn it into a type. So you can say that something that has the type of Na in par with something that has the type of Cl reduces to something that has the type of NaCl. And so the connection between this stochastic behavior and types gives you an even deeper level of predictive power and an ability to produce explanations, which is not present in machine learning.
Yeah, this definitely sounds much better than not knowing.
Yeah, absolutely. That's the real problem, is that the machine learning is going to be incredibly brittle, right? There will be all these edge cases, and we won't know where the edge cases are because we don't know why it makes the decisions that it does. And yes, that could be fun and exciting, but it could also be incredibly frustrating, especially if you have some human at the edge and all the human can do is interact with this AI program, and it's brittle at some case that is life-threatening to the user.
Yeah. I was thinking, like far in the future, if we are just continuing in that way, we will have some kind of, a global belief, oh, this is happening because of God said something, and God is, some machine. And basically, I mean, what is the difference, right?
Yeah, you're absolutely right. Yeah, you're absolutely right. So this is why I have been so vocal about the use of this machinery, because it leads us down a different path than the machine learning does. But now, so I want to take another step. Now you've understood So the rationale and the motivation. And by the way, if you want to play with this, you certainly can. There is a machine called SPIM. This is Stochastic Pi machine, which Andrew Phillips developed at Microsoft Research. And he applies it to the modeling of biological systems. The thing is 15 years old. Go check it out. You don't have to believe me. There are just tons and tons and tons of research in this direction. But what hasn't happened is people haven't thought about taking it out of fundamental biology and chemistry research and moving it over into enterprise resource planning.
One of the aspects that would be very interesting, say, in case of something like a post, is not just the analysis of how that particular post is being touched by different people and all that, but what is the generative nature doing? For example, if there are responses to that post that are exploding or going in a particular way, analysis of that generative aspect of a post, in addition to the analytics around what is happening with the post itself, would be interesting. Is that
Great. Yes,
capturable, or is that a
absolutely?
You need more than stochastics or for that?
No, that fits entirely within the framework I'm describing.
Okay.
Entirely within the framework. All right. So now that we understand the motivations, let's begin to talk about some of the mechanics. So one of the biggest technical challenges is to come up with a good stochastic model. And there's been active research on this, and there's several different pieces of the puzzle that one has to solve. First you need to assign a probability distribution based upon rates of reaction, right? So for a given channel, for example, you can associate a rate of reaction, and then you have to go from that channel. So you might have a process sending on the channel and a process receiving on the same channel, and then you associate to that channel or type of channel a reaction rate. And then you want to associate the rates across a population of channels with a probability distribution for interaction. And you need some notion of scope around that, right? Because that begins to be more global, right? So you can't have a notion of rate unless you have some scope in which you can understand the competition for possible COM events. And that fits very naturally onto RChain's notion of shard. So the shard is the scope around which we have a bunch of physical resources that are going to decide on the allocation of computational resources. And that's where you can implement or naturally rest this interpretation of the stochastic or probabilistic, the probability distribution that is given to associated rates. And notice that this is already a part of the RChain architecture. You can think of the cost accounting as a mapping from a rate function to a probability distribution on COM events. So the extent to which validators are going to serve given smart contracts, deployments based upon how much flow is associated with that deployment, gives you a stochastic interpretation. Does that make sense? Do people understand what I'm talking about here?
Yes, I mean you're basically saying just by matching channels in the in a normal way, as we will have some additional rules which channel can be matched, or which when COM events can happen or not, even if.
No, what I'm saying is the fact that we've implemented cost accounting on top of the channel matching. We don't allow channel matching. We don't allow COM events without spending flow, right? And the distribution of flow assigned to a given contract is already giving you a stochastic interpretation.
Yeah, that was an important piece right there.
And the consequence is some rewrite will happen or not, right?
That's correct. Right. So we're getting a probabilist. We're already with the architecture of our chain. We're already getting this. Okay. So I just want to say that the challenge that comes with giving a probability, associating a probability distribution with a notion of rates across channels fits exactly with our chain's architecture by design, because I've been thinking about this for 20 years. But there's more to the story. Okay. So the next piece of the puzzle is that there are different notions of probability distributions. So Shapiro and Silverman's and later Priami's notions of stochastic pi were shown to have certain desiderata that they suffered. And so later, Cardelli and Mardare produce another flavor of probability distribution. I won't go into the technical details of why they consider it superior. I recommend that you go look at the papers. But I want to say that for myself, I have thought about probability distributions themselves, and I guess I don't believe in the one form versions of probability distributions as much as I believe in the two norm versions of probability distributions. So essentially, you can think about how you want to accumulate your different probabilities, and so you can accumulate them just by summing, or you can accumulate by summing the squares and taking the square root. So that's the two norm. So if you sum the squares and take the square root, then you have the potential of taking square roots of negative numbers. And so essentially what you get is a notion of complex amplitudes and negative probabilities. And if you go look at Scott Aronson's work on negative probabilities, basically what he shows is that you can give a completely consistent mathematical theory that turns out to also be quantum mechanics without thinking about quantum mechanics at all, and just working out the theory of probability where you can have negative probabilities. And then what happens is that the negative probabilities give you cancellation along certain paths, right? Because you sum up some negative probabilities with some positive probabilities, and that's what gives you the strange, weird correlation that we find in quantum mechanics. So my argument is that this form of probability theory, when coupled to a physical interpretation has been tested scientifically to 30 decimal points of accuracy. So I would prefer to use that one over one where we know the probability distributions have been sorely misused and often do not correspond at all to physical interpretations. So again, this is bias, and I'm being open and honest about my bias, but it's bias towards what's the most heavily tested notion of probability that has been applied in physical circumstances, and that is the two-norm-based probability theory, which also happens to have an interpretation in terms of quantum mechanics. So does that make sense? Do you understand the shape of the argument? You don't have to understand all the details. You just have to understand like why I'm biased towards a particular kind of probability, notion of probability, and the corresponding notions of distributions.
Well, I mean, I wonder if the choice between the square of errors based probability versus errors based probability is a matter of the application. I mean, I don't know if it's always the right thing. For example, you take the stock market prices, and if the purpose there is profit optimization, and you worry about the negative movements in the stock, you care about that error, but something going up is not a concern necessarily. So it is, and I don't know how. We don't
know that there aren't correlations, right? And what we've seen is that the models drift from the behavior all the time. Essentially, the models are narratives, they're fictional narratives. And this is why you have had many chaotic behaviors in the stock market that were completely blindsided all of the modelers.
Yeah, right, but in that case, though, how would you figure out if the square-based? I mean, I can see the square-based methodology being correct if your goal is perhaps prediction, but if your goal is optimization of profits, I'm not so sure that you necessarily need the square-based.
I mean, I definitely think that you can do, and in fact, like people do optimization-based calculations, minimum entropy kinds of things, all the time in the quantum mechanics setting. That's just it's part and parcel of the toolkit there.
Yeah, I mean, I personally think both those models are completely are mostly useless as opposed to say like a Bayesian.
But again,
updating probability.
Yeah, but that's also different, right? So Bayesian versus frequentist is about epistemology versus ontology. So I'm not going to go into the belief part of things in this round of discussion. So there is a notion of what we know and updating what we know, and it's very important that the Bayes rule and the frequentist calculation correspond. If they didn't correspond, then you'd have this terrible gap between what you know and how you know it, and the actual behavior of the system at large deviations. But this is epistemology versus ontology, and I'm not going to go down that path just now. I just want to get something that corresponds to experiment. That's it. Things that have been applied to physical experiment again and again for decades, well, centuries now, and have high degree of accuracy. That's what that's what I want to base the architecture on. So with that said, then the technical problem, oh, by the way, your comments are well taken and important, but I want to go carefully when we make those considerations. But so with the next step then is, if we're going to use a 2-norm based probability distribution, then what we have to do is we have to make an assignment of a let's say the covector to input and the vector to output, so that we can take the application of the covector, so we can basically do a Boron rule style probability. So that's what I'm working on, which is to give a consistent Boron rule style interpretation of how of the probability of a given COM event. Does that make sense?
It makes sense. I'm not exactly sure what is Boron rule, but
the Boron rule says that to get the probability, you take the bra and the cat and you square it, and that gives you the probability. So we're going to associate a bra, right? So using Dirac notation, there's a bra and a cat, and then potentially an operator in sandwiched in between. But to get the probability, you take the bra, operator, cat, and you square that, and that's your probability. So if we're going to do this for COM events, we're going to associate a bra with input, a cat with output, and then potentially some operator in between. And that's going to give us the probability distribution of that particular COM event. Or not the probability distribution, but the probability of that particular COM event. So that's what I'm working on to provide a notion of probability. And then the final piece of the puzzle is completing the interpretation of that style of 2-norm based probability, aka quantum mechanics, into rho itself. So that's more researchy, but the idea is that we can take all of those calculations and give a natural interpretation in terms of the rho calculus itself. So I've presented that on several occasions. So that still has work to be done, and it's not necessary to get an enterprise grade system. But this is the overarching architecture. It's like, now that we have in our hands a linearly scalable system, what we then want to do is to provide enterprises. In other words, large scale systems. It's not necessarily enterprises. I just use that as a code word for large scale operations where you have some kind of mission critical thing riding on it. The ability to do end-to-end global view system planning.
So basically, running the computation, we will get information from inside what is needed for the hardware to run the computation itself.
We'll get that, but also you can go the other way. The probability distributions that you want to ensure certain end-to-end behavior can be used to generate economic policy. And that was the reason I pointed out that we already have a probability distribution that comes from the flow governance of the COM events. So you can go the other way and say, okay, this probability distribution gives me this end-to-end behavior, so therefore I have to have this much flow associated with these kinds of COM events. Right, so it gives you a tool to enforce particular economic policy. And you can say why. We want this economic policy because during Christmas we have to get these kinds of packages through the system.
Or we want to know like some kind of insurance policy.
Yeah.
What is optimal and yeah.
Exactly. That's exactly right. So this is the other class of motivations that I've had for the architecture that we've been rolling out, and why I have been so confident about our architecture. It's 8 o'clock, so we have to go, but I'll make one last point and then go. So the other technical challenge that needs to be addressed when one is moving to the probabilistic or stochastic view of these calculi is what is the appropriate notion of bisimulation? And that is an open research question. Nobody, I mean, there are some interesting directions. There's some very smart people who put forward some interesting proposals, but there isn't, to the best of my knowledge, a communal consensus around what the right notion of bisimulation is in the probabilistic setting. And nobody, to the best of my knowledge, has considered the right notion of bisimulation in a two-norm probability setting. All right, with that, thank you very, very much for your time and attention, and look forward to chatting with you next week.
Thank you, Greg.
Thanks.
Great explanations. We appreciate it.
Yeah.
Cheers.